There are many data science workflows that people have come up with, but I'm particularly fond of this one. It is pronounced OSEMN, and it stands for Obtain, Scrub, Explore, Model, and Interpret. Now, one shouldn't take this workflow too literally. One does not generally go from step 1 through step 5 in a perfectly linear order. And also, each of the steps are sometimes involved with one another. But it's a kind of a good way to get a bird's eye view of what's going on in data science. And it does generally flow in this direction. So in the first case, we need to obtain our data set. Can't do data science without data. And that is often more difficult than people realize coming into data science. A big part of our work is often just about obtaining the data. So in this tutorial, we'll have a couple very simple, easy examples, but I'm also going to deal with one slightly more complex example, although still somewhat simple compared to what is dealt with in the real world. Then the next step is often scrubbing. Sometimes you can skip over this if you're particularly lucky and your data is in perfect, shiny condition. But a lot of times we need to do some scrubbing before we can actually do anything interesting with our data. And sometimes in the process of scrubbing, you might discover that your data is garbage and you need to go out and obtain more. The next step is explore, basically looking at your data and seeing what you've got. A lot of novice data scientists think that they can skip this step and go straight to modeling. But the fact is that your model isn't going to make any sense if you don't know what you're dealing with. Exploring is, in my mind, actually arguably the most important part of data science, along with interpret at the end. Modeling often gets the most press, but I think it's the exploring where a lot of the interesting insights come. And as before, as you're exploring, you might discover, there's some junk, there's something that I need to fix. You might need to go back and scrub, or maybe even go back and obtain more data. Once you've come to some conclusions based on your exploration, or maybe not conclusions, but hypotheses or ideas, you might go on to the next step, which is modeling, where you try to formally test your theories. So exploration might give you some ideas. Modeling will allow you to test those ideas out and maybe take them to the next step of actually doing prediction. Prediction is one of the main things that people do in data science, although it's not the only thing. And sometimes you might actually just be satisfied with what you get out of your exploration. You might not even do any formal modeling. That's also perfectly fine sometimes. And then finally, interpret. Sometimes people don't realize the importance of interpretation. Sometimes the interpretation is not that important. If your job is simply to surface which stories are should appear in your Facebook feed, for example, interpreting why the algorithm produces the results that it does maybe isn't that important. But a lot of times it is. A lot of times, basically, people will want to know why things are the way that they are. And that is something that requires a uniquely human component. So I'm going to go through each of these steps in sort of a rapid fashion in a way to kind of get that full soup to nuts idea of what data science is using Python. So first we're going to obtain our data. You might obtain your data through a variety of means. There are a couple built-in ways that are pretty convenient. Scikit-Learn has a datasets submodule that has actually a number of built-in datasets and also allows you to parse existing datasets that you might have on disk into a way that's very good for Scikit-Learn. For this tutorial, we're going to use the infamous Iris dataset that's been used, that was invented by Fisher and has been used by statisticians and data scientists for many decades. And we're also going to use the pandas.io.data submodule, which, similar to Scikit-Learn's datasets module, allows you to grab data from, in this case, it's grabbing data from the web. You can also get your data from CSVs, from SQL, from a SQL database. SQL database is maybe the single largest source of data for data science, if you were to take all the different formats. We're not actually going to deal with SQL in this tutorial, but it's worth noting. APIs is another method. In fact, pandas.io.data actually uses an API. But you might use other APIs. So, for example, if you want to use Facebook or Twitter data or New York Times, or many websites have APIs where you can get data. Again, we're not going to deal with that in this tutorial, but it's good to know that it's out there. And then there's hundreds of other ways you can get data. So starting off with Scikit-Learn, we can get data using this iris dataset. We can get this iris dataset, and we can see if we look at iris.descr, description, basically, we can get a description of what our data are. So this is the iris plants database, and it tells us a bit about our characteristics. So we have 150 instances, 50 in each of 3 classes. So basically what this means is that we have 3 classes of irises, 150 instances, that is 150 specimens, if you will. We have 4 attributes for each instance. These are 4 numeric attributes which we will use to predict our class. Those attributes are the sepal length and width and petal length and width, all measured in centimeters. And these are our 4 classes. They are all irises. They are the Setosa, Versicolor, and Virginica classes. Now I apologize if my Latin pronunciation is poor, but I suppose this will all be transcribed, so that doesn't matter. So we have summary statistics, which we're going to get again down below, but this is kind of a good way to kind of know what we're getting into. We see that our sepal length and width, the min and the max for each of these, the standard deviation, hopefully you already know what standard deviation is, and the class correlation. We're not going to worry about this quite yet. And then so on and so forth, some citation where it's been used. It's been used since 1936, apparently. And you'll see it in pretty much every textbook about statistics and data science. So here are our feature names. This is given to us by Scikit-Learn. It's very handy that Scikit-Learn gives us the feature names right off the bat. And we can also take a look at the data. We're looking at the first 5 rows of our data. We don't want to look at all 150 because that would take over the whole notebook. But what we see, we have got 4 columns corresponding to these 4 feature names. And then we have each row is an observation, is a specimen, if you will. So the first specimen has 5.1 centimeter sepal length, 3.5 width, 1.4 centimeter petal length, 0.2 centimeter petal width, etc. So all of these first 5 have a petal width of 0.2 centimeters. Okay, so that's our iris data set. We're going to be coming back to it later, but just to kind of, oh, actually, sorry, we're still dealing with it. So I like to use pandas. Most data scientists who are using Python these days use pandas quite a bit. Pandas is a really nice, convenient way to dealing with data. Scikit-Learn doesn't know about pandas, so you need to actually fit the data from Scikit-Learn's dataset into a pandas data frame. So what we see here, this is an array. And we have all these numbers here, but the data here doesn't, corresponds with this. We know this, but it's not built into the data set. What we can do by putting this into a data frame is we can say the data is, for our data, we're using iris.data, which is our array, and the column names we're getting from the feature names. And this allows us to put labels on our columns. So here we see our petal width, 0.2, etc., etc. Pandas data frames are very flexible, and we can add columns in much the same way that we would add a new item to a Python dictionary. So simply that naming the new column and giving it the data. So in this case, what we're going to do, what I'm doing here is a little bit tricky. I'm actually taking, we have iris, we have our iris target names. Sorry, this is jumping around so much. We have our iris target names, which is Setosa, Versicolor, or Virginica. Those are the 3 species of irises. And then we have our iris target, which is an array of integers. So 0 corresponds to Setosa, 1 corresponds to Versicolor, and 2 corresponds to Virginica. The reason why they do this in Scikit-Learn is because they want we want everything to be a number. Scikit-Learn doesn't know how to deal with anything other than numbers. But for human readable purposes, we might want to turn these target numbers back into their names. So the way we can do that is actually pretty simple. Each one of these integers is an index for the target name. So 0, as I said, corresponds to Setosa. And what happens when we call iris target names and feed it the iris.target is it refers, each number gets converted into the names that we want. So that allows us to give this nice human readable extra column for our species. This is not strictly necessary for what we're doing, but I just wanted to show you how you can do that and how it can be handy. So our data frame is, of course, a data frame. It's also worth noting, if you're new to pandas, that each column is a series. So a series is to a data frame what a vector is to a matrix. It's one-dimensional, and what we have is we have a lot of each series and data frames all have a lot of methods associated with them that are very useful. Another neat thing about pandas is that we can refer to columns in this way that's kind of similar to how you refer to a key in a Python dictionary. But so long as the column name doesn't have any spaces or special characters, and so long as it doesn't conflict with other methods or properties, it will actually become a property of the data frame, which is really nice because then you can do things like tab completion. So I can type in iris df, make sure that I've run this. Oops, I need to define my data frame. Okay. So I can go ahead and call iris df and then hit tab, and it will give me all the methods and properties of the data frame, including species. So I can actually use tab complete to get species, which is really convenient. Now notice this won't work for the other ones. This won't work for sepal length and width and so on because of the space and the parentheses here. So I have to, if I want to reference those columns, I have to reference them in this way with by name. So I could do sepal length. Is there a space there? Yes, cm, and that will give me that. Okay, so that's a bit of pandas, a bit of scikit-learn. Let me show you another way that you can get data using pandas directly. Pandas has a data reader, which allows you to get stock data. So I'm going to go ahead and run this. And what this does is I'm getting all of Facebook's stock ticker data from Yahoo. And so Yahoo Finance keeps a record of all the open, close, all this information, high, low, etc., the volume of each trade per day. So if you're interested in doing stock analysis, this can be very handy. I'm going to go ahead and pause now because I seem to have an internet. Oh, here we go. Okay, never mind. Here we go. So we have our data reader, and I can. Another neat thing, if you're new to IPython, is you can get information like this. So if I want to find out more about data reader, I just type it in, give it a question mark, and I can get things like the what I can put in here. So this allows me to get data from a number of online sources. That includes Yahoo Finance, Google Finance, St. Louis Fed, and Kenneth French's data library. So I believe these are all financial data sources of one form or another. So here we specify which data source we're using, and here we can say what we want from the data set, from the data source. We can also specify start and end times. I didn't do that in this case because Facebook is so young as a public company that I don't mind getting all of it. But if I wanted to do something like forward, I might want to limit that. So this, here we get the open, the high, the low, the close, and the volume, and also the adjusted close, which in this case is always equal to the close. So moving on, I can take a look at the count of each column by calling fb.count. fb is the name of my data frame, and count is a method. A lot of methods exist for both data frames and series. So if I call fb.count, I'm calling the data frame, the count method from the data frame, and I get to see what the count is for each column. I can also call the individual column and call count, and that will give me the same information for that specific column. Okay, moving on. So now I'm going to get data from a CSV. This data is not quite as nice and clean as the data that we get from the built-in Python APIs. And in this case, it's okay, but whenever dealing with data in this form, you always have to watch out for all kinds of nasty things like Unicode errors and things like that. Fortunately, we don't have any Unicode errors, although we do have some things like this, which we'll clean up later, and when we get to the scrubbing stage, where the ampersand has been represented as ampersand amp semicolon. You might have seen that before if you've done a lot of stuff with the web. We are going to want to clean that up. So first thing that we do, we go ahead and load the CSV, and Pandas read CSV works pretty well. It does a good job of guessing what is needed in order to get the data in here. And it has a lot of optional parameters. In fact, it has loads of them. If we go to read CSV question mark, we can see it has all of these optional arguments. So we can change the separator. By default, it's a comma, hence comma separated values. But if you're using something else where it's pipe delimited, you could change that. That's fine. It has all these different ways of doing quotes and escape characters. It will infer that there's a header, but you can change that so that, say, you want to specify which row has the header information, or that you don't want to give it a header at all. There is a lot going on here, and I encourage you to take a look at it later. This parse dates argument is particularly useful if you're dealing with dates. A lot of times Pandas will actually guess how to interpret the date correctly, but if you find out that it's not, this is a good way to override that. So moving on. We're also going to use a second set of data. We've got our country regions, which tells us our country code and the region code, so and the region name for each of these countries. We're also going to look at life expectancy data. I can't remember where this data comes from originally, but I got it from the Flowing Data website for one of their tutorials. I think it comes from World Health Organization or something like that. So here we go. Basically we've got information for each country as well as the world, along with a code, 3-letter code for each one. And what is the life expectancy of for each of these regions from 1960 on to 2009. Now I also wanted to show you how you can specify an index column here. Just as before I mentioned you could specify a header row, you can specify an index column. So here, just to sort of show that in action, I'm saying that I want my country name, the country name column, to be the index. So here's my index, and I can refer to things by the index. Indices are handy for merging and for quick references. For a data set, this is actually a relatively small data set, so the index won't really help much with the speed increase, but with larger data sets, choosing something smart for your index can really help. So you can merge data frames in a way that's very similar to how you do a join in SQL. There's actually two ways of doing this. One is with the merge method, and the other is with the join method. We're going to start with the merge method. So the merge method, you can do it in a number of different ways, but the way I like to do it is I use one data frame, then in this case life, so this is my life expectancy data, and then I call the merge method on it, and the first argument to the merge method is going to be the second data frame that I'm going to merge with life. Then I can specify left on, which says what is the column in the left data frame that I'm going to use to merge. In this case, it's going to be country code. There's a space, notice that. And then right on, which is the column in regions that I will be merging on, which is country code without a space. Now, if there had not been a space here, that actually would have been a lot more convenient, because then these two names would have been the same, and pandas could have actually guessed that that is how I want to merge it. But because of this space, I have to explicitly specify my left on and my right on. So I'm creating this new data frame, which I'm calling life reg. That's a concatenation of life and regions. And I get the head. And one of the things that you'll notice here is world has disappeared. This is because world does not exist in regions. So this tells us that what we're dealing with here is actually, it's called an inner join. Those of you who have SQL experience will be familiar with that. And what that means is that only rows that exist in both columns, in both data frames, will appear in the final output. So what we have is we have our country code, we have all of our columns for each year, and then we have our country code again. Notice that we have the country code twice because they have two different names. If they had the same name, they would have been combined into a single column. Then we also have the region code and region name. All of this we're getting from our region data frame. So this is cool because now that we can go ahead and say in Afghanistan, AFG, in 1960 the life expectancy was 31.436. In 2009 it was 47.756. Afghanistan is in South Asia. So this will become handy later. So for our first exercise, what I want you to do is look at, reload the data from country regions, but this time set the index column to country code. This will be, and also reload data / life expectancy cleaned, and this time set the index column to country code. Now this time also I want you to do a join instead of a merge, and one of the things that's neat about this is that because we've set our index columns explicitly when we're loading in the data, we can use a join without needing to specify how we're going to join it, because join will automatically assume that we want to join on the index, and since we set the index as our join key, that will happen magically. We'll notice some interesting differences. One big difference that you'll see if you do this is that we hold on to world this time. So notice last time when we did the merge, we lost world because it didn't exist in our region data frame. This time when we do our join, and we on the left hand side we have life, we will hold on to world. But what it's going to give us is nans, that stands for not a number, which is basically a null or a none, for region code and region name, because these did not occur in the region data frame. So this is what is called, this is essentially an outer join, in this case a left outer join. meaning that we include everything in our left data frame, whether or not it occurs in our right data frame, and we just fill in the gaps with these NaNs. Okay, I'm going to pause there so that I can get a glass of water. All right, we're going to continue where we left off with scrubbing the data. So we just loaded in a bunch of data. We've now have we have our iris data, we have our Facebook stock data, and we now have this merged data set from life expectancy and regions, basically. So South Asia, Europe, etc. So we're going to play with some of these. Now, actually, for scrubbing, we don't the data that we got from Scikit-Learn and from pandas doesn't need any scrubbing. It's already been pre-cleaned. But part of the reason why I wanted to use this life expectancy data is that it has some interesting things that require some scrubbing. You might need to scrub for all kinds of reasons. One that is pointed out in the dataist article I referenced at the beginning is that you might have equivalent categories that might be represented differently. So, for example, New York City and NYC are the same place. Of course, Python is not going to know that. You need to tell Python that those are the same place. So that would happen in the scrubbing stage. In our case, one of the things that we have to deal with a few things. One of them is we have all these nans, these not a number parts in our data. What's happened is that for some of our countries and regions, in this case for world, we only have data for once every 5 years up to a certain point. In the later part, we have it for every year, 2000, 2001. But in the beginning, we have a lot of missing data. Now, what you do with missing data, there's not one answer. It really depends on what you're trying to do. But a lot of times, you can get away with simply dropping the data. So if you do life, say life is the name of our data frame, of course, and we call the drop NA method, what it does is it drops all rows with missing values. So we drop world because world has missing values. We keep Afghanistan, Albania, Algeria, etc., because these all have data for the entire series from 1960 to 2009. One thing I want to draw your attention to with this, and this is true with many, if not most of the functions that Pandas has, is that what drop NA does is it doesn't actually change the data frame. What it does is it returns a version of the data frame without the missing values. So if we call this, we get the top 5 rows of our data frame without NAs. But if we go back and look at the original, it's still there. We haven't actually changed anything. This is something to be aware of and to be careful about when working with Python. Python is it's an object-oriented language with some functional characteristics, but it does, and it's not always consistent in how it does things. So, for example, if you call the sort method, it will actually change the data frame. But if you use the sorted function, it won't change the underlying data structure. So this is something that you need to be aware of and just be careful of. If you're going to change your underlying structure, you want to do so with care because you might want to undo that at some point. So just be aware of that. So it's often preferable to transform data from a short, wide format into a long, skinny format. What does that mean? So this is in a short, wide format. We have every year is a column. We have as many rows as we have countries. So this is sort of a mock-up of what this looks like. We have our country codes. We have 1960, 1961, etc., to 2009. What we actually want is something that looks more like this, where we have each country code and each year as 2 columns, and then the life expectancy as a 3rd column. So this is going from short and wide to long and skinny. There's a number of reasons why we might want to do this, which we will get to later. But first, I just want to show you why, or how you would do it. So we're going to be doing a lot of changes, and you don't have to follow this particular pattern, but I'm doing this for educational purposes so that we can kind of look at each step. So the first thing that we're going to do is make a copy. I don't want to ruin my original data frame, so I'm going to make a copy of it. The next thing that I'm going to do is I'm going to set the country code. So actually, let me run this. I'm going to set the country code to be the index. So now what I've got is I've got my country code is my index. My country code used to be, actually I'll go ahead and add this. So when I originally had this, my country name was the index and the country code was just another column. Now what I've done is, since I did it this way, what I've ended up doing is setting the country code setting the index to the country code, which wipes out the country name. I don't actually care about the country name at this point. But if you did the exercise and you reloaded the life expectancy data, setting index call equal to country code up here, your data frame will actually still have the country name as a column. So be aware of that, because that's going to change what comes next. All right, so going ahead, we've got our country code as our index now, and now what happens as a result is that all of our columns are the years. Now I put this code in here, which is not necessary at this point because of the way that I did my data frame. I don't need to get rid of the country name, but if I did, say if I go back up here and reload this data, this time setting country code as the index, I'll go ahead and do that up here. So I'm actually going to set life to A to country code. What that's going to do is, notice I have country code here and country name here. I can go ahead and set my index to country code. Actually, I can't send my index to country code because I already did that. So I'm going to clear results. Okay, so clean that up a little bit. So now what I have to do is, because I have this column that I don't want, I'm going to have to skip over it. So the way I'm going to skip over that is I'm going to use this iloc, that's index location. And index location allows you to use matrix and array type indexing. So we've got the first before the comma are the rows that I want, and after the comma are the columns that I want. So I just want to skip over this first column because this has the country name, and I want to get rid of that. So I'm just going to, because I just want 1960 through 2009. I just want years. I don't want that other garbage. And then what I do is I'm going to go ahead and stack that data. Might have to do this. So what I've got now is I've actually got a series. I've turned my two-dimensional data frame into a one-dimensional series, but my series has this kind of interesting quality in that it has what's called a multi-index. So the multi-index includes the country code and the year. You notice the country code is labeled, but the year is not, because nowhere in here is the year actually labeled as a year. It's simply each year is its own column. So if I go ahead and look at 2b.index, what I have is a multi-index with two levels. The first level is the country code, and the second level is the year. So what the names of these. So one thing that I want to do is I actually want to turn my series. I want to actually break the index out and turn those back into columns. Remember, what I really want is this long, narrow data frame. I do want it as a data frame. And I want code to be a column, I want year to be a column, and I want life to be a column. I'm not concerned with my index here. So I want to break the index out of being an index and back into being columns. And I can do that with this reset index function, which is pretty handy. So that will break that out, and it remembers that my country code is called country code. But it doesn't have a label for this, so it's just going to call it level 1, nor does it have a label for my data, so that's going to be 0. So what I really want is, I want this data, I like the way it is, I just need to rename the columns. I'm going to use country code without the space, so that I can join it with my, my region data later. I'm going to label this second column year, and I'm going to label the third column life expectancy, and I'm going to maintain this camel case convention. No spaces, capital E for expectancy. All right, so that's all nice and good. Let me go ahead and run those. I'm not sure if I ran them already. And then another thing that I might want to check is see if I have any nulls. Now, one thing that's kind of interesting about this is that by redoing this, by reshaping the data in this way, I've actually gotten rid of my null values. Notice that world goes straight from 1960 to 1965. So now, later on, we might want to, this is not actually how we want to do it, but I wanted to show you that this is one reason why having this long skinny format is helpful, is that it actually provides us with a little bit more flexibility with what we have and what we don't. So here for 1961, having 1961 as a column means that every region needs to have a value for 1961, and if it doesn't, it has to fill it with not a number, which can mess things up. But with this long skinny format, we actually can have years that don't have data. We'll just skip them. So we have 1960, 1965, and so on. And then once we get to the 80s, we have one for every year. So that we've managed to get rid of our nulls without getting rid of any data this time. Now, another thing that I want to mention is notice what happened to our data types. Country code is an object. That basically means object is kind of a catch-all. In this case, it's a string. But notice that year also is an object. Now, we don't want that. We want our year to be a number. We want it to be an integer, so that we can do some math on it later on. So the easiest way to do that, to fix that, is to actually map the int function onto year. So we can call the data frame, we can call the column out of the data frame using this dot notation that I like so much, and then we call map. This is one of the most useful things in data frames, if you ask me, that you can just map a function onto an entire data frame, or onto an entire column, I should say. What the in function does is it will attempt to cast each value into an integer, which in this case is perfectly fine. Now, I want to also draw attention to the fact that if I had not done this part up here, where I drop the country name column, this function would not have worked, because what it would have tried to do is it would have tried to call the int function on strings like world and Afghanistan, because that would have been considered to be the first item. So what we did with our stack is we took each column and turned it into a row. And by dropping the first column country name, our first column is 1960. That's good, and that's what we have here. But if we had not done that, then country name would have been the first column, and then that would have also made it the first row for each country, and that would have caused this to crash. So we don't want that. So that's why we got rid of it. And I'll mention, at the beginning I talked about looping back, that you don't always go in a strictly linear fashion. As a matter of fact, when I was constructing this, I didn't realize that year had was not of an integer format. It was actually that it was a string, and that messed me up down the way. So I had to go back and do the scrubbing and fix that, make year into an integer. So yeah, you won't get everything right the first time, and that's totally fine. Okay, so that's our life data set. That's great. Now let's go on to our regions data set. Here we don't have any problem with nulls. We can see that by calling this isNull function on the data frame and summing it. So what isNull does is it will return true if there's a null value in there and false otherwise. And then what sum does is it will essentially count all the ones, all the trues. True is when you call a function like sum is looking for integers or for numerics. The numerical value of true is 1, the numerical value of false is 0. So when you sum a series of true-false statements, what you're getting is the count of trues. So we can tell from this that we have no null values. That's great. But we do have this ugly ampersand thing, which just drives me crazy. So I want to get rid of that. So I'm going to call, now each region name is a string, and I can reference it as a string, and then call this replace function. Replace is a string function that, that is built into Python, and that allows you to replace one substring with another substring. So it will look for all the occurrences of this amp string and replace it with just the ampersand symbol. And by doing it in this way, this is functionally equivalent to what we had up here with our map. But since we're using a kind of a fundamental string function, we don't actually have to use the map. We can just do it this way, which is kind of nice and terse. I also hate this all income levels thing. Okay, first of all, let me finish that. So this, actually I don't need to, I'm going to go ahead and destroy that. And I can run this, and so I gotten rid of all the ampersands, but I also hate this all income levels thing. This is just not helpful. So I want to drop that, and I'm going to use the same str.replace function and put in this, and what I'm replacing it with is a empty string. All right, pop quiz. Why do you suppose I have a slash here? Give up? Because string.replace, str.replace, actually what it's taking is a regular expression. Now up here, treating this as a regular expression was totally fine. But here, parentheses are considered special characters in regular expressions. They indicate something. And so this parentheses will be interpreted by the replace function if you don't put an escape character before it. This backslash is the proper escape character for strings in Python, for regular expressions. And what this backslash says is interpret what comes after it as a literal string. Don't interpret it. Don't try to turn it into something else. So this backslash open parentheses is treated like just a straight up open parentheses. So that allows me to get rid of all this all income levels garbage, and now I've got much nicer, cleaner names that are much easier to read. Okay, we're good now. We've cleaned up our life data, we've cleaned up our regions data, and I'm going to go ahead and do my merge. Isn't that nice? And so now what I've got is I've got my country code, I've got my year, I've got my life expectancy, I've got my region code, and my region name. And I've got 9483. I've got 9,483 data points in each column. Now, if there had been missing data, some of these numbers might have been lower, but we have data for each column at this point. Okay, the next step is going to be, the next exercise is to redo everything above, but this time I do want you to drop the NA first. I want you to get rid of the world data. And the other, actually, not so much, it's actually not the world data that I'm so concerned about, because we dropped the world data here with our merge, because it doesn't appear in the regions data. This is an inner join. So we're dropping the world data. But there are some other countries in regions that have missing data, and that's going to mess us up down the line. So I actually want to, I do want to drop the missing values. I want this to be, I want every year to have a data point in this data set. So I want you to go ahead and redo the above, but this time call drop NA before you do the reshaping. All right, I'm going to take a break now. All right, let's pick up with step 3 in our 5-part series on the data science workflow. So this is Explore. Explore we're actually going to cover in 2 parts. The first part is descriptive statistics, and the second part is visualization. So as I say here, the describe method is your friend. Use it liberally. For every method, every time you load a data frame, every time you do anything with it, any major transformation with the data frame, it's always good to go ahead and call the describe function. It will tell you about what you're dealing with, and it will tell you right away if there's major problems. It will notify you of that. So we'll see you have it'll tell you the count of each column. We have 743 all along the board. Notice here it has 7.43 times 10 to the second power. I'll explain why in a moment. It also gives you the mean, the standard deviation, the quartiles. This is all useful descriptive information. Here we have the same thing for the iris data frame. And you'll notice that we've seen this. We've seen these data before when we first loaded the iris data frame at the very top. This time we're getting it from the data itself. Now normally you won't have that nice sheet that tells you all about your data, so you'll want to use the describe function to get that. Now going back to what I was saying about why is this in scientific format, and this is why does this have so many trailing zeros? The reason why is because pandas will format each column in the same way. So because the mean here is this kind of long, fairly long decimal point number, 49.50425517, it will go ahead and format everything in a way that is consistent with that. There's a sort of a hierarchy of how you want to represent numbers. And at the top of that hierarchy is scientific notation. So here we have 5.0811703 times 10 to the 7th power. So because these are very large numbers, it's best to represent these in scientific notation, which means that the whole column needs to be in scientific notation. So that's annoying. So one way that we can kind of fix that is to do a transpose. So all this does is it just turns this data frame on its side like this. And when we do that, all the counts, since all the counts are integers, it will represent the counts as integers. So that makes this a lot easier to read than 150.0000000. It also does the same for these guys. These are all floating point numbers, but they only have 1 and 2 level precision. We don't need all these trailing zeros at the end. For the mean and the standard deviation, that will be displayed appropriately with this high level of precision. So I often like to call describe.t. It's not necessary, but it makes things a little bit easier. Now one thing you'll notice that is missing is the species column here. So why is the species column missing? Well, notice that we have all these rows for count, mean, standard deviation, min, and our species column is our strings. They're Versicolor, they're Setosa, etc. You can't do a standard deviation of a string, so it won't include that in the output here. Those of you coming from R might find that annoying because R will give you descriptions of the non-numeric columns, partially because R is not constrained in that way. The output of summary in R doesn't return a data frame, whereas in Pandas the describe function returns a data frame, so it needs to be consistent in that way. However, you can call the describe function on non-numeric columns. You just have to do it individually. So for example, here I'm calling irisdf.species.describe, and that tells me that it will tell me the information that it can give me about this column. For example, the fact that there are 150 items. That's the same as what we saw up here. It tells us that there are 3 unique values. Now that's something that we don't get from here because these are numeric numbers, and generally we don't care about the uniqueness of numbers, but we do care about the uniqueness of strings. This tells us that we have 3 unique strings. These are our 3 classes. Now it also tells us that the top string is setosa. Now in our case, all 3 species are equally represented, so the top is not meaningful. But if we had class imbalance, this would tell us what our biggest class was, and it also tells us the frequency of that class. So that can tell us if we have, especially if we have some like major class imbalance where we have 50 uniques, but one of them counts for 50% of what we're looking at, or something like that. So that can be helpful. Now I want to show you how to create a mask. Masks are very useful in dealing with pandas data frames. They allow you to reference only a portion of the data frame. So we'll create kind of a simple mask here where I want to focus only on irises with a sepal width less than or equal to 3. So we'll notice that the first one that comes out false, the next true, and so on. So the length of this mask is 150, but some are true and some are false. Now I picked 3 because 3 is the median, so this will give me half of what I'm looking for. So if I go ahead and do sepal width.count, that'll give me 150. If I do sepal width.sum, it'll give me 83 actually, because I guess there are a few. There's with the less than or equal. I guess it's slightly more than half. I can use that mask when I'm applying. I can apply that mask to a data frame just by putting it in these brackets. So this is kind of like indexing, only instead of an index, it's a series with true and false values, and it will only give me back the values where it's true. So this gives me item 1, that's this one right here. Remember, Python is 0 based, so don't let that fool you. 8, 12, 13, 25. These are all the ones with the sepal width less than or equal to 3.0. All right, for the first exercise, I want you to create a mask with Versicolor and describe the features for that species on its own, and do the same for Setosa and Virginica. I'm not going to pause at this point, I'm just going to keep on going. So another way that you can do something similar to that, where if you have, rather than doing the masks, which we will be using later, but I do want to also show you another way that you can do that with class categories like species, is you can do a group by. So we have 3 unique species, we discovered that from up here, and we can group by them and compute a mean, which allows us to look at the mean sepal length and width and petal length and width for each species, rather than for the whole kit and caboodle, which we saw up here. So this is very handy sometimes. Another thing that you can, with the group by, you can call all kinds of these functions, all the data frame functions, including mean and quantile and so on. So if you want to do quantile, you might want to take a look at pd.series.quantile, which is where the function actually comes from, which will tell you how to actually compute it. So if you want to get the 95th percentile, what you need to do is set the q equal to 0.95. I'll let you do that as an exercise to the reader. All right, that is descriptive statistics, numeric statistics. Now I'm going to go into visualization. Everybody loves visualization. So when doing visualization in IPython, Notebook, you want to make sure to run this %matplotlib inline. This is very, very important. A lot of times if you forget to do that, what will happen is you will run a visualization and it will return, but you won't see anything. And the reason why is that matplotlib, remember that matplotlib was designed before IPython Notebook existed, and before IPython Notebook, everybody did Python from the command line. And the command line isn't very good at visualizing data. So the way that matplotlib works and worked is it has to render through an external library. If you're running from the command line, what this does is it pops up a window and allows you to see the visualization there. But since we're using a web notebook, we want to have our visualizations right in line. Now, you might ask, well, we know that we're using IPython Notebook. Why doesn't this just happen automatically? There's some technical reasons for that that have to do with IPython wanting to be able to be kernel agnostic. Actually, it's not even IPython anymore. It's Jupyter. Jupyter standing for Julia, Python, and R. So the idea is that you can use Jupyter with Python, Julia, R, or any number of other things. And something about that that flexibility requires us not to make assumptions about how to use libraries like matplotlib. But we are using Python and we are using matplotlib, so we're going to go ahead and use matplotlib inline, which will allow us to view our plots inline. So the pandas data frame, in addition to having a lot of convenience methods like count and describe, also have some really cool plotting functions, including boxplot. So this is a way of doing something kind of similar to what we were doing up here, where we did a group by mean, or we also did the same thing here with a pivot table. I definitely recommend you look at pivot tables that allow you to group by some column and then pick another column that you want it to represent. So in this case, what we're going to do is we're going to look at the distribution of the sepal length for each species. So we see for Setosa, the sepal length has a mean around 5 and ranges between 4 point something and 5 point something. For Versicolor, it's somewhat higher. For Virginica, it's somewhat higher still. There's still a lot of overlap here, but we can see the trend is definitely, definitely does seem to be a difference. Histograms are even better. So the problem with box plots is that the nice thing is that they can give us kind of this nice distribution, but they do assume a certain amount of normality to our distribution, whereas maybe our distribution is not normal at all. For example, here we have this bimodal distribution for petal length and for petal width. And if we just did a box plot of all the petal lengths, we would not see that. Now this is not separated by group, however. You'll notice that these are the distributions for all the irises. We can group by the species, but if we do that, then we have to specify what column we're going to focus on. So we can again go back and look at the sepal length by species like we did here, but this time we're going to look at it as histograms, and so we'll get 3 different histograms, one for each species, and we can see the distributions thusly. Another function that's really useful is the plot method. This is particularly useful for time series. It does assume that the index is time, generally, and it will just plot out that value. So in this case, we're plotting the close over time, and this is the Facebook closing price, as you can see over time going. It's kind of sticking around $25 for the first up until looks like fall of 2013, and then it starts going up. Now we can plot multiple columns as well by naming them. thusly, and thus we're referencing each column that we want to plot. Now in this case, the visualization is not so interesting because, as you would expect, all four of these values track very closely to one another. But this sort of gives you a sense of what you can do with this. We can also chain functions together. So you can say take volume, call the cumulative sum function on it, which will give you a running total, and then plot that. So that's really cool. That allows you to sort of see the volume of stock traded over time, the grand total of all the transactions. But for cumulative sums like this, you probably really shouldn't plot it as a line. You probably want to plot it as an area. So you can actually specify that as the kind of plot that you're going to make. So that's pretty nice. Now, that can only take you so far, however. These functions that come built into Pandas data frames, really useful. I recommend that you use them a lot, but at a certain point you might hit your limit of what you can do because they just didn't build what you want to do into the Pandas library. So maybe you're like me and you hate scientific notation. You find it confusing, and you like to see those zeros. It's easier in the eye. It's much easier to tell 9 zeros from 7 zeros than it is to tell e to the negative 9, negative 7 versus negative 9, or whatever. So I can force that by, the first thing I do is I do the same thing I did before. I did this volume cum sum dot plot kind area. Now I want to mention something. Notice that at the end up here I've had a semicolon. What the semicolon does is it suppresses the output. It suppresses what this returns. So we just get this nice plot without any garbage. But here I didn't put the semicolon there, and I did that to show you something, because when I just call this function, what it does is, in addition to making this visualization, it also returns this object, this axis subplot object, and I can do something with that. I can set this valuable fig to equal that plot, and then I can play with it. So this is a matplotlib object, and as a matplotlib object, it has properties like y-axis, and y-axis is an object itself, which has this method called setMajorFormatter, which means tell me how to format the major tick marks. There are no minor tick marks in this case, so we're just going to use the major formatter. Now I'm also going to use the func formatter. There's a few formatters in Matplotlib. I'm going to use the plt for matplotlib.pyplot. I'm going to use the plt.func formatter to dictate how I want my numbers to be formatted. And here I'm going to use this string format function. This is a fairly uniquely Python way of formatting strings. It is a little foreign to people who are coming from C and Java, and Python does support C-style string formatting, but I recommend looking into how to do this style of string formatting with these curly braces. Just Google Python string formatting. It's much more flexible, it's much more powerful, and it is the preferred way of doing string formatting in Python. So what I'm doing here is this curly bracket says this is where my number is going to go. The colon says everything after this is going to tell how I want to format the number. The comma says I want comma separated. That I want these to have commas every 3 digits. And then the 0.0f means I want nothing after the decimal point. So that gives me these, nice big numbers that are, maybe tell me more than this way of doing things. Now, if you're somebody who is perfectly happy with scientific notation, then that's fine. This is really just to show you how you can change things. You could also do the same thing, actually, incidentally, for the date format. You can change the date format if you say you want to make this, you don't like the fact that this is, these are all English shorthand for these months. Maybe you want to have a more international style, then you should do that. Okay, moving on. I can plot two functions against one another. I can plot open and close, and that will give me the two time series. But say what I actually want is a scatter plot. Well, I can do that too. In this case, what I'm going to do is a little different. I'm going to call the plot method off of the data frame and tell it that the kind of plot I want is a scatter plot. And I want to set my x to open and my y to close, and that will give me this nice open to close scatter plot. And of course, it is extremely linear, as you would expect. So as an exercise, I'd like you to do the same thing, do a scatter plot using the iris data set, but plot the sepal length against the sepal width and see what you get. Okay, assuming you've done that. Something that I want to point out is that a data frame is really a wrapper around a NumPy array. Now we saw that back in the beginning when I first created this iris df data frame, the way I constructed it was by feeding it a NumPy array and then telling it what the column names were. This was reversible. In fact, if you call the dot values property off of any data frame object, what you'll get is an array. And this is very useful because a lot of times Pandas is a fairly new library. A lot of Python libraries don't know how to deal with data frames, and including Scikit-Learn sometimes trips up on data frames. So you might want to access the underlying array and feed that into something. So this is one way that you can do that. So I also want you to repeat the last exercise, but this time use the NumPy index notation instead of referencing the columns by name. Okay, the next step, histograms. I already talked about how much I love histograms, but the problem is that Pandas is a little bit limited in how it can plot histograms. So this is an example of how you can plot histograms entirely using matplotlib. First, I want to draw attention to this part, which I haven't touched upon before, which is from __ future _ import division. What does that mean? Well, this from future, we're using Python 2. As you probably know, there's also something called Python 3. Python 3 has not yet been widely adopted, despite the fact that it's been around for quite a few years now. But we can grab stuff from Python 3 and put them into Python 2. And that's what this from future does. It's a special way of getting Python 3 behavior in Python 2. And the specific behavior from Python 3 that I want is that division will always division will produce a decimal value. Now in Python 2, by default, if you divide two integers, you will always get an integer, and that integer will actually be the floor of the division. So if you divide 1 by 2, you won't get a half, you'll get 0. But if what I want is a half, I have two options. One is I can explicitly cast all of my integers as floats, which is tedious and annoying, and it's easy to forget to do that. Or I can just go to the future and import division, which will automatically promote integers to floating point numbers when necessary during division. So I want to plot, just to give an example, I'm going to plot a histogram of what is the predicted IQ, given that the IQ is supposed to be centered on 100 and have a standard deviation of 15. This is not a comment on the validity of IQ. This is just for demonstration purposes. Anyway, so I've got my mu and my sigma. I'm going to add a bunch of random numbers. I get this from NumPy. A couple conventions here that I've been using, you might have noticed, is shortening NumPy to NP, pandas to PD, matplotlib.pyplot to PLT. These are all conventions that you'll see over and over again in different tutorials and different bits of code that you might come across. So I'm using numpy random.rand n, meaning that I want n random numbers, normally distributed, and I want 10,000 of them. I'm gonna create a histogram, which will do this plot for me, and it will also return n, which is the values, the bins, and the patches. The n is the values in each bin, and so on. And then I want to add labels like X label and Y label and a title, and I want to give a little text up here saying mu and sigma, mu equals 100, sigma equals 15. The things you might notice is this is kind of neat. We've got some LaTeX here. LaTeX allows you to do mathematical notations, so I can do /mu, and that'll give me this nice mu symbol. Another thing you might notice is this R. Why is there an R here? Well, when doing strings in Python, if you just leave it alone, it will treat it as an ASCII string, but it will also it might interpret some things for you. So for example, we talked earlier about using C-type string formatting. Dollar signs are kind of special characters. Now, you can use R to say, I want to interpret this. I don't want to interpret this string. I want the string to be what it is. A dollar sign is a dollar sign. A slash is a slash. This backslash is not a escape character to be interpreted by Python. What it actually is it's a symbol that is used by LaTeX. So the backslash mu is the mu symbol. Backslash sigma is the sigma symbol. This will be interpreted by matplotlib when it's doing its LaTeX formatting. We don't want it interpreted by Python, so that's why we have this R at the beginning. Anything else about this? Yes, we want a grid, etc., etc. Very nice. Okay. Now, one of the things so the next exercise that I want you to do is to overplot the sepal length of each of the three species, masking one species at a time. So remember at the beginning, I wanted you to make some masks for each species. Now you're gonna go ahead and use those masks, and the masks will help you plot the different widths one at a time. Where am I? Okay, I got lost. Sorry. And hint, use alpha to make the histograms semi-transparent. Okay, I'm going to take a break here. All right, going to continue on with the modeling portion of this data science workflow. So we've already done a lot of, we've obtained our data, we have scrubbed it, we scrubbed out the missing values, we cleaned up some of the strings in our region information, and we've done a lot of exploration. We've done both done some numeric descriptive statistics, things like getting the mean and the standard deviation, and we've done some visualization with plots, with box plots, scatter plots, histograms, etc. These are all things that you'll want to go more deeply into, but this is kind of an intro. So we'll have some resources at the end to help you go deeper into some of that stuff. But I want to go on to the next stage, which is modeling. Now, modeling is a very large area in data science, and it can be very simple or very complex. So probably the simplest approach to modeling is often about looking at relationships between different values. So far we've been looking primarily at single columns at a time, or we did a scatter plot which looked at two columns at a time, and we saw that that some values might be correlated with one another. So how do we measure that? How do we model the actual relationship? Well, the first way that we might do that is through doing things like correlation. Pearson's product moment correlation coefficient, for example. This is the most popular way of measuring the relationship between two values. So we can get a correlation matrix very easily just from our data frame. Our pandas data frame has this correlation function. As I said before, pandas data frames have all kinds of neat methods and properties that you should definitely play around with. One of them is correlation, and we can see how each value correlates to one another. Now we see again, as before, the species column is left out because it's not numeric. You can't do a correlation between a numeric column and a non-numeric column. But for our numeric columns, we see this nice matrix. So along the diagonal is, of course, 1. Everything is 100% correlated with itself. But then we also see that the sepal length and sepal width have a negative correlation of negative 0.109. Sepal length and petal length have a correlation of 0.87, and so on. And petal width and petal length, of course, have the highest correlation of all. So that'll give us the R values, the correlation coefficients. But one of the problems with correlation coefficients and a lot of these statistics, these sorts of statistics, is that we don't know how likely is it to get, say negative 0.42. Right? The negative correlation between sepal width and petal length is negative 0.42. Is that likely or not? It's less than half, or it's less. R can range between negative 1 and 1. So what does that tell us? Well, SciPy has this stats library, which is really good at things like that. So we can go ahead and call the stats.pearsonr, and we can give it our two columns, sepal width and petal length, and we see that we have an R value of 0.421. We got that up here. We already knew that. And then we also have this P value of 8.43 times 10 to the negative 8th. Now that is a tiny number. And what does that mean? Well, you probably remember from your stats class that a p-value is the measure of the likelihood, the probability of getting a value like that under the null hypothesis. Well, what's the null hypothesis? The null hypothesis is that these two things have no relationship with one another, but that they are normally distributed around some central mean. So if the sepal width and petal length are both normally distributed and have no relationship with one another, well, in a perfect world, you would get an R of 0. That would be no correlation. But of course, you're never going to get exactly 0. Because of just randomness, you probably get something a little bit positive or a little bit negative. So the question is, given that you observe this correlation of negative 0.42, how likely could that have happened by chance if there had in reality been no relationship between the two numbers? And that gives you this p-value of 8.43 times 10 to the negative 8th, which means that there's that percentage of likelihood of getting that result by chance without there being any actual relationship. So what this tells us is that it's extremely unlikely, given this information, that we would have seen a relationship like that randomly, which suggests, does not prove, but suggests that there really is a real relationship between these two. So that's Pearson's R. We can also perform independent t-tests. So, for example, let's say we're interested in with t-tests you can only compare two categories, so we'll just compare these two categories, Virginica and Setosa. We'll leave out Versicolor for now. And I want to see how does the sepal width compare between these two? Are they different or are they the same? So this is what an independent t-test tells us, is we give it two data sets, two series, or vectors really, and we see, are these two different or the same? And we get a t-score, which is negative 6.29, which tells us that there's a significant difference between the two, and then this p-value tells us the likelihood of seeing that difference, again, by chance. So I want you to remember what a p-value is, because it's something that trips people up a lot, and you got to study it, and it's a little bit funny because it's essentially a double negative. You're saying how unlikely is it how unlikely is this result to happen if under the null hypothesis? How so we're basically saying that it's incredibly unlikely that you would see a difference like this, like negative 6.29, by chance. So that tells us that there really is a very large difference in the sepal width between Virginica and Setosa species. So we can also do linear regression. Linear regression allows us to go a little bit further and look at actual relationships between two sets of numbers in order to see how they relate. Now, if I want to do linear regression to see the way Virginica or one of these species affects the sepal width, I need to do a little bit of pre-processing. So remember what I said about how Scikit-Learn, and this is not just Scikit-Learn, this is SciPy, all these libraries, they're not very good at dealing with strings generally. They want to see arrays of numbers. So if I want to do something with a species, it's okay if I want to do a mask up here like this, but if I want to feed this data directly into something like linear regression, I have to what's called get dummies. So that means that I turn these species into 3 different columns. I have three species. These turn into 3 columns, and each column is 1 where that value is true and 0 where it's false. So we'll see all the Setosas have 1 for Setosa and 0 for Versicolor and Virginica, and all the Versicolors have 1 for Versicolor and 0 for Setosa and Virginica, etc., etc. So we can do this with this get dummies, calling get dummies on the species. And so what this will produce is just this part. So that turns the Setosa, Versicolor, Virginica, etc. And I can also do the tail so you can see what the end looks like. And then I'm going to use my join, which you're now familiar with from our the scrubbing part of this lesson, to join these dummies to our original data frame. Now, the join does not change the data frame. What it does is it returns a new data frame, and that's what I've got here, my IrisDF2, which has my original IrisDF, which is these 5 columns, and then these 3 that I got from the get dummies command. Now, for our linear regression, just to keep things simple, I only want to look at, again, the Setosa and Virginica. I'm going to leave Versicolor out. And so the way that I'm going to do that is I'm going to create a mask where Versicolor is less than 1, basically saying Versicolor is 0. It's not Versicolor. And I'm only going to pick those rows where this is true. That is where Versicolor is false. So this is everything that is not Versicolor. That is, it's all the Setosa and all the Virginica. So I got my not Versicolor Virginica. And I'm going to set that as my x. That's my exogenous variable. That's my independent variable. That's my predictive variable. There's a million names for this. And then my y is going to be my sepal width. That's what it is that I'm trying to predict. That's my dependent variable, my endogenous variable, etc. And so I'm going to call stats.linRegress on my x and my y, and it gives me 5 values back. The 5 values are the beta, that's the coefficient that is assigned to my x. I is the intercept. So if you're familiar with linear regression, you know what the intercept is. The r is the r value, which represents this relationship, and you'll notice that the r value is negative 0.536, which is the same. Oh no, sorry, we don't have it up here. But what it is the correlation coefficient between the x and the y. And the p-value, and then we also have an e for our epsilon, which is basically our standard deviation around, sorry, not our standard deviation, our standard error. So this gives us our confidence interval. So we can actually turn these values into our estimated function, which is basically y hat, I just did this in ASCII, so there's no hats. But anyway, y hat equals 3.418, that's our intercept. Now this is plus minus, it's a little confusing because the beta actually turned out to be minus. So what it is minus 0.444 plus or minus 0.138, we get that from our error, times x. So that tells us more or less what the relationship is between x and y. If, in other words, if the flower is virginica, that is, virginica is 1, because virginica is true, then the sepal width will be 0.444 smaller than if it were a setosa, right? Hopefully that it made sense. So we can also use, I'm a really big fan of Seabourn. Seabourn is it's a plotting library. It actually builds off of Matplotlib. Part of what I like about it is that it is, because it extends Matplotlib, you can use all the Matplotlib functions, but it provides some things that are really convenient. So for example, to do a plot like this in Matplotlib would require, probably 5-10 lines of code. Whereas here we can do it in just one by using this LM plot. That's linear model plot. And for the LM plot is limited in much the same way that the stats linear regress is limited. We can only give it one x and one y. Well, all linear models have only one y. So this is only for simple linear regression. Although if you look into it, there are some pretty neat things you can do for other variables, but we'll leave that out for now. And then we give it our data frame. And this shows us the linear relationship between virginica, that is, whether or not the flower is virginica or setosa. So virginica 1 equals that it is virginica 0 is that it isn't, and the sepal width. And we see this negative linear relationship. So if you're virginica, you have a smaller sepal width. Now the problem is that because these are binary values, binary classes, 0 and 1, we have this sort of overplotting problem where dots kind of are stacked on top of one another. So we can fix that with this X jitter, which will jitter the dots a little bit from side to side. Very useful in these class cases. So we can get a nice cloud of our virginica flowers and our setosa flowers. This is only aesthetic. It does not change the data at all. It is just so that you can kind of more easily see what's going on here. Okay, let's try another one. Let's try our Facebook low and volume. So does a low price change the volume of trades? Well, what we see is that first of all, the intercept is very high. Just the standard is very high, but in fact there is there's actually a very negative relationship between the two. So if the low price is low, that will increase the volume. If the low price is high, that will decrease the volume, which makes sense, right? People will probably trade more when the stock is cheaper, and this is our relationship. So we see it slopes slightly downward. The R value is negative, but it's not hugely negative, but it is very significant. So this is a very small p-value. That's 9.17 times 10 to the negative 6th power. So that's 6 zeros coming off to the left here. So even though it has a fairly, like, this R value is not that far from 0, it's only negative 0.16, it's still very significant. However, if you look at the plot, and this is part of why you should always plot your data, you can see, let me go back for a second. You can see, that, why is this not coming up? Oh, I forgot to do the not Versicolor. There we go. Okay, great. So if we go ahead and plot this, we see that if we look at the residuals here, and I can go ahead and actually do a resid plot. there seems to be some skew here. This doesn't seem to be totally centered on 0. Now remember, one of the assumptions for doing a linear model is that the error will be normally distributed, and this does not look normally distributed. We have these positive outliers. We don't have any negative outliers. So that should kind of make you skeptical of whether or not this linear model is a very good model, but we'll leave it at that, and you can talk to your local statistician to find out more about that. Okay, so let's go on. Every stats course, Stats 101 course typically ends with ANOVA, so we will end with ANOVA as well. ANOVA allows you to compare multiple categories. ANOVA is useful for a number of things, but the thing that we're going to focus on is comparing multiple categories. So we have 3 species. So far up here, we've only been looking at 2 species at a time, Versicolor and Setosa, sorry, Virginica and Setosa, leaving out Versicolor because we can't do a t-test with 3 classes. But we can do an ANOVA with 3 classes. So that's what we're going to do here. We're going to do our species Setosa, Versicolor, Virginica. We're going to stick with sepal width because that's what we've been doing. And we can go ahead and run that, and we see we have this F value and this P value. F value, in case you forgot, is an F score is a ratio of 2 variances, which is why we call this ANOVA, an analysis of variance. And this allows us to look at the degree to which our model, which uses these 3 values to predict sepal width, how much that model is able to explain compared to the variance within groups. So it's between groups and within group variance. Now this 47.36, this is kind of a difficult number to interpret because it actually is very much dependent on what are called the degrees of freedom of our model. So I typically skip the p-value, the f-value, and go straight for the p-value in this case. And we see that this p-value is incredibly small, which means that you would not see this relationship by chance. It means that the sepal width is definitely dependent upon the species. It doesn't mean that you will know the sepal width down to a t because you know the species, but just that the species definitely carries information, tells you a lot about the sepal width. And we can visualize that with this factor plots. Factor plots are useful for this sort of thing. What we've got here is we've got our 3 species, Setosa, Versicolor, and Virginica, and we've got the sepal width, and along with these nice confidence interval bars, and we can see that indeed these are 3 different classes. So that is super cool. All right, exercise. Using our life expectancy data. Apply linear regression where x equals year and y equals life expectancy. What is the coefficient or the beta of the year? In other words, on the whole, how much does life expectancy go up every year? Now this will go back to why were we messing around with the data back in the scrub section? Why were we transforming our data from this wide fat format to this long skinny format? Well, this is why. Because we want to use year as an explanatory factor. We couldn't have done that before. We couldn't have done that where year was a different column each time. But when we turn those columns all into one column and we set that becomes our year column, we can use that as a factor. And what we want to do is we want to try to explain life expectancy by the year. And then let's also do a factor plot where this time we're going to keep y as life expectancy. That's still the value that we're interested in predicting. But we want to do where x equals region. So basically, we want to do a kind of ANOVA, but mostly focus on the plot because that's what I find most interesting. Is do a factor plot where we get to see each region mapped out and what is the life expectancy. So which regions have the greatest life expectancy and which have the lowest. And I have this hint here to set x tick labels rotation equals 90. How you're going to do that, you're going to do that the same way that we did up here when we wanted to change the y-axis set major formatter. This time what we're going to do is we're going to do that to the x-axis. And the reason why we want to do that is that if we don't do that, the names of the regions are going to run into each other. Here we only have three species, so there's a nice big gap between each one. But when we have 6 or 8 or however many regions that we have, they'll start to collide with each other and it'll be impossible to read. So if we just change the rotation to 90, they'll line up this way and it'll be much easier to read what each life expectancy is, sorry, what each region is. All right, for the last step, the last stage, we don't really have much of a tutorial here. In fact, don't really have much of anything, except that this is an exercise to the student. So basically, at this point, when we get to the interpret stage, there's not really a whole lot that our computers can do for us. Our computers have already given us p-values. They've given us f values, t values, r values, all these great values. And the question is, what do they mean? What does it mean to have a p-value of 1.33 times 10 to the negative 16th? What does it mean to have an r value of negative 0.536? This is the interpretations part. So traditionally we said that a p-value of less than 0.05 is quote-unquote significant. That is, that there is a less than 5% chance of seeing such a result by chance. That is, if the null hypothesis had been true. Now there are some problems with this notion, but for now we'll take it as gospel, and we'll say that's simply the way it is. And so for the exercise, I want you to to do the Pearson-Czar. That's the what we did at the beginning here, where we do stats Pearson-Czar, and calculate that for the sepal width and petal length. Is it positive or negative? And what does it mean? What does it mean that the correlation coefficient is positive versus negative? And do the sepal width and the petal length, and same thing, but is it significant? And then do the same thing for sepal width and sepal length. So basically the idea here is just to make sure that you are actually able to interpret what SciPy gives you. Do these numbers make sense? Unfortunately, this is not something that can easily be done in a tutorial like this, but you might want to check your answers with somebody who knows more about stats. There are some great tutorials online on Matplotlib, SciPy, Pandas, and Seabourn. I recommend you study them all closely. Seabourn has tons of really cool functions like lmplot, factor plot, violin plot, all these neat things that let you do nice visualizations. Pandas, as I said, also has tons of great functions. SciPy is a huge library, and then beyond SciPy, there are other libraries like stats models and Scikit-Learn, which both go even deeper into a lot of this stuff. Stats models is meant for more interpretive statistics, focuses a lot on things like p-values, goodness of fit measures. It's more for people who have a traditional stats background. And Scikit-Learn is a machine learning library that will allow you to do cool things like random forests and support vector machines and all kinds of crazy fun stuff like that. And then Matplotlib, I'll be honest, I'm not a huge fan of Matplotlib, but it is the foundation of plotting in Python. Now there are alternatives. For example, there's Bokeh, which you might want to look at. Bokeh is kind of neat. It's fairly new. It allows you to actually make interactive plots. They are trying to stay closer to the grammar of graphics, which is, for those of you who are coming from R, If you're familiar with ggplot, that's where the GG and ggplot comes from, grammar of graphics. Bokeh is not nearly as close to that ideal as ggplot is, but it is nice in a lot of ways. And then you can make cool plots like this. Let's see if this works. Sort of. Anyway, good enough. So I hope you enjoyed this tutorial, and let's continue the conversation in the comments.